You're trapped inside a room controlled by a mathematician demon. The demon sets up a square table with 4 buttons at its corners. Each button could be either on or off, but you don't know the state of the buttons by looking, touching, or any other way. The demon secretly sets the initial configuration of each button. Any configuration is possible. Then you play in rounds, and in each round you press simultaneously any subset of buttons you want. Pressing a button will flip its state, but remember, you have no idea what that state is. But after you played your move, the demon secretly rotates the table at a multiple of 90 degrees. You have no idea by how much, could be even 0 degrees. The game proceeds until all 4 buttons are on. Then the door in the room automatically opens and you could leave. If that never happens, you will be trapped in the room forever. Can you find a strategy that will guarantee that at some point all 4 buttons will be on? That means even if the demon knows your strategy in advance. If you want to think about it yourself, now is your chance. I want you to think about such a game. You don't know how the table starts and what the current state is. And not only that, if you press a button on your next move, that same button could be anywhere, so you can't really know which buttons you've pressed. And you need to have a finite strategy that will always work, not statistically, not sometimes after an infinite number of steps, but always work. How is that even possible? The first thing we can do is think of a simpler version of the problem. Instead of having 4 buttons at the corners of a rotating square, we have just 2 buttons at the corners of a rotating line. This should be easier to solve because we have just 3 options: pressing the right button, the left button, or pressing both of them. But if you think about it, since the table keeps rotating, we cannot differentiate between pressing the left button or the right button, because we don't know if button A is on the left or if it's B. So let's arbitrarily decide we only press the left button. Now how can we solve the problem using only these 2 moves? Feel free to pause the video and think about it. Since we can't change the state of specifically button A or button B, we should look at the combined state of the buttons, whether they are in the same state or different states. We will say that a pair of buttons is correlated if they have the same state and uncorrelated otherwise. First, if they are correlated, it could be both on or both off. If it's both on, we're done. Otherwise, we can press both of them and finish. Therefore, in the case that the 2 buttons are correlated, pressing both of them solves the table. Second, if the 2 buttons are uncorrelated, we could press any one of them so they become correlated, and then we could use our previous move to win. To conclude, we get this strategy for solving the 2 button case. Let's see again that it works. The table could start in one of these 4 states, we don't know which one. But actually one of them is an automatic win. We start by pressing both buttons, after which we win if the buttons were correlated in the beginning. Now we remain with buttons which are uncorrelated. We press one of them to make them correlated. And finally, repeating the first move, we finish the strategy with a guaranteed win. It's not easy to see how to generalize the solution from 2 buttons to 4. The key idea is also to distinguish between 2 cases. The buttons are correlated or uncorrelated. But which buttons? Not all 4 at once, but in pairs of 2, so we could use the solution to the 2 buttons recursively. There are 3 ways to divide the 4 buttons into 2 pairs. Can you think which one we should use? We'll choose the diagonal pairing because it's unaffected by the table rotations. We can always know which button is paired to which. We use the same approach as in the 2 button case. First, if each diagonal is correlated, it's easy to reduce the problem to the 2 button case. Why this is easy? Because we can imagine each diagonal as a single button and solve the problem using our solution to the 2 button problem. That means pressing a button in the 2 button problem corresponds to pressing a diagonal in the 4 button problem. So we can solve the square table using the 2 button strategy by translating every move according to this equivalence. And this is how we translate each move explicitly. Now let's look at the case where the diagonals are uncorrelated. Since we already know how to solve a table with correlated diagonals, we can have a simpler goal of just correlate them. But how can we do it? We also want to use the 2 button problem recursively. However, since our goal is not to turn all the buttons on, but to correlate the diagonals, so now each button represents a diagonal, and a button being on and off represents a diagonal being correlated or not, green if correlated and red if not. Now we need to translate the moves. Pressing a single button corresponds to changing the correlation of a diagonal, which could be achieved by pressing one button from the diagonal. And pressing both buttons corresponds to changing both diagonals' correlation, which could be achieved by pressing two adjacent buttons. Note that no matter the table's orientation, two adjacent buttons are always one from each diagonal. Therefore, this strategy guarantees that after some step, not necessarily the last, the diagonals will be correlated. Now we need to combine our two strategies to a single strategy that solves the table problem. A naive approach could be just applying them one after the other, but as we said before, we only have a guarantee that at some point the diagonals will be correlated, not necessarily at the end of the last step. Therefore, we need to perform the second strategy after each step of the first strategy, because we don't know when the diagonals will be correlated. See that after each step from the green strategy, we need to do all the steps of the blue strategy. Also, if the table happens to start with correlated diagonals, we need to try and solve it before we start messing up the correlation of the diagonals. That gives us a total of 15 moves for the solution. One last point which you can verify by yourselves is that the blue strategy doesn't change the correlation of the diagonals, so it does not interfere with the green strategy. And that's it. This is the solution to the problem. Now you can exit the room and escape the demon. But personally, I don't feel like this is it. I feel as if I've stopped watching a series after the first season. It kind of feels like an ending, but the story isn't complete. And if you feel the same way, you probably know where I'm going with this. We talked about solving a linear table and how to use its solution for solving a square table. We should now ask ourselves, can we use a solution to the square table to solve another regular polygon table? If you think about an octagonal table, you're correct. It works exactly the same as in the square table. We start with correlating the diagonals. Each octagon's diagonal corresponds to a button in the square. On and off in the square corresponds to correlated or uncorrelated diagonal in the octagon. And so pressing a square button corresponds to pressing just one button in the octagon's diagonal. And if the diagonals are correlated, we'll solve the table by treating each octagon's diagonal as a single button in the square. And so pressing a square button corresponds to pressing both buttons in the octagon's diagonal. We then combine the two sub-strategies into a final strategy, exactly like we did in the 4-button case. This idea could be easily extended also to 16-sided table and 32-sided table, and in fact for every 2 to the power of k-sided table. But how many steps our strategy takes? Let's denote by n the size of the table, and f of n is the number of steps. Both the blue and green strategy takes f of n over 2 steps, because both of them were constructed from a solution to a table of size n over 2. So we have f of n over 2 steps for the green strategy, and so the blue strategy is repeated f of n over 2 plus 1 times, where each repetition is f of n over 2. We have f of 2 equals 3, which is our base case, as we saw in the 2-button strategy. We can prove by induction that it equals to this closed form formula. But wait, this number is not just any number. It's the optimal number of steps any strategy can have. And why is that? Because we have 2 to the power of n starting configurations, minus 1 because they all on state is an automatic win. They all must be solved at some point in our strategy, but think about 2 games where the table doesn't rotate at all. If we use the same strategy, then at the end of each step the 2 tables must be different. That's why they can't be both solved at the end of the same step. And that's why any strategy needs at least 2 to the power of n minus 1 steps to solve 2 to the power of n minus 1 starting configurations. And amazingly, we match this lower bound. Now we are ready for the final chapter, in which we ask ourselves, what if the table size is not a power of 2? Let's start with the simplest case, a triangular table, and let's consider a non-trivial starting configuration. In order to solve it, at some point these two buttons need to be in the same state. In a single move we can press either 1, 2 or 3 buttons. If we press one button, the daemon can rotate the table such that we always miss our two target buttons. Similarly, if we press two buttons, we could always press both target buttons, which won't change them to the same state. And of course, to press all three buttons isn't going to help either. And if you think that maybe we could succeed in the first move before the table rotates, that move won't work on every possible starting configuration. And that's why there is no winning strategy for a triangular table. Well, not every table size is solvable. Let's try to apply the same technique to a bigger table, a pentagonal table for example. We'll take two buttons in different states and try to find a move that will change them to be in the same state. Let's try pressing two adjacent buttons. But if the daemon rotates the table like this, it won't work. We pressed both of them. In fact, in general, any move with two adjacent buttons pressed isn't good. So maybe this move. Well, if the table is rotated like this, it won't work. We pressed none of them. In fact, any move with a gap of two unpressed adjacent buttons isn't good. These two rules can be simplified to pressing exactly one button for every two adjacent buttons. So if we want to construct a move that changes our target buttons to be in the same state, we must press every other button. We can start and construct such a move, but at the last button we see we're stuck. Whether we select it or not, we will violate the constraint. That means we cannot construct such a move, and therefore our two target buttons will always remain in different states, so there isn't a winning strategy to a pentagonal table. The nice thing about this argument is that it works for any odd number. There's nothing special about 5. So in fact, every odd-sized table is impossible to solve. To complete our journey with this problem, we need to figure out what about even-sized tables which are not powers of 2. In this case, let's write the table size as n equals m times k, where k is an odd number. The key idea is to see that such a table contains m subtables of size k. For example, in a table of size 6, we have m equals 2 and k equals 3, so 2 copies of a triangular table. In a table of size 10, we have 2 copies of a 5-sided table. And in a 12-sided table, we have 4 copies of a triangular table. Why is that helpful? Because if we could solve the problem on the n-sided table, we could solve the problem on a k-sided table. To see why this is true, we assume we have a strategy on a table of size n and we play on a table of size k, for example 6 and 3. Our strategy to k equals 3 could be identical to that of n equals 6, only each move in the 6-sided table is projected to the subtable of size 3. So we just imagine a 6-sided table around our 3-sided table and solve it exactly the same. But since k is odd, we proved it's impossible to solve, so that's a contradiction. That's why we cannot have a winning strategy to the n-sided table. Now, to wrap things up, I want you to think about the journey we had with this problem. We started with a seemingly impossible problem, and we've achieved a far greater understanding of the problem than originally intended. Because not only we solved the problem for a square table, but for every 2 to the power of n-sided table, with the minimum steps possible. And not only that, we showed that for every other table size, there is no winning strategy. In my opinion, these results reinforce the feeling that the key ideas we had for solving the problem are fundamental to the problem. And if you find this problem intriguing, like I do, I encourage you to ask more questions. What if we have a 3-dimensional table, or even a higher dimension? And what if instead of rotating, the table does something else between steps, like reflecting around some axis? Maybe one of those questions will shed new light on the problem, one which we haven't seen yet.